All right, time for a little bit of theory of probability. Hope it's been a good weekend for you all. I've been thinking pretty carefully about how to end the semester, and one thing I wanted to get to was at least a presentation of the central limit theorem. But I also wanted to take a little bit deeper of a dive with you all. And one of the topics that I think is sort of helpful to think through. At least I discovered this to be the case as I took a deeper dive myself in graduate school and did a fair amount of reading on my own, is the topic of order statistics. Order statistics. There is a section in chapter 6 of your book that deals with this exclusively. But in my opinion, the way that they cover it is unnecessarily laden with notation and complexities. And as such, I wanted to give you kind of, more of a first principles approach to order statistics, look at it together, and hopefully this will make a little bit more sense than the section as it's presented in the book itself. The way they do it in the book is they do a lot of approximations and whatnot. I'm just not sure that it's the most helpful lucid explanation of what's going on. Hopefully what I do here will be a little bit more helpful to that end. I may or may not accomplish that goal, but we shall see. This lecture will be exclusively delivered right here in the whiteboard format, just because I'm going to intermingle a fair amount of computation. It didn't really make a lot of sense to me to have a slide development of that particular or of these particular computations, just because it's kind of nice to be able to follow along as the computations are being done. All right, so again, this is kind of toward the tail end of chapter 6. I think there may even be a problem or two that deal with order statistics. There is a problem that I was talking to Matthew about that is slightly related to this order statistic business. It had to do with selection of bugs in a region, but you didn't have to do that problem using order statistic theory necessarily. Okay, and just one more word before we dive in here. I will on Wednesday. I'll probably do something similar to what I did last week, where this material here and any prior material, I will assign a problem that I select from the homework set as is articulated in the syllabus, and I will have you complete that in about a 24 or like a 48-hour turnaround by Friday. Same kind of rhythm that we've been doing lately. Okay. All right. So let's jump in here. So we're going to talk about order statistics. Okay. So order statistics. Okay. So the setup here is that I have a bunch of independent, identically distributed random variables. So we have n independent, identically distributed. That means they all come from the same distribution, and they're independent of one another. We know what that means. And by the way, that term, independent, identically distributed, comes up so much that it gets its own little acronym. Okay, it's just IID. Random variables, x1 ... through xn. Okay, I don't care what distribution they're from, as long as, by the way, I'm going to assume that these are continuous random variables. Okay, but other than that, I don't care what distribution they come from. There is a way to develop this whole theory in the discrete context also, but we're just going to be talking about continuous, the continuous situation, right? And so we're going to assume that and continuous. Okay. Okay, so that's the other assumption that we're going to make. Okay, what are order statistics? Well, they are these. Okay, so you define, Okay, so here we go, define. Okay, y1 equal to, remember, so x1 through xn are random variables. And by the way, the reason that we assume continuity, like that these are continuous random variables, is we really want the probability of them being equal to each other to be essentially 0, okay? Now we can go to the discrete case and say, well, you know, we're gonna relax that just slightly, but it does make for a fair amount more complication, okay? So that's one reason we want these to be continuous, because we want the probability of them being equal to any pair of these being equal to be 0, okay? So you're gonna define y1 to be the smallest among x1 through xn. And by the way, that is well defined, because you know that the probability of any of them being equal is 0. Okay, y2 is going to be the second smallest among these things. Okay, dot 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 all the way down to yn, which is the nth smallest, which is kind of a dumb way of saying the largest. It's the largest among, you know, x1 through xn. So clearly we have y1 less than y2 less than dot 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 less than yn. And the y's are built from the x's, okay? These guys right here are called the order statistics. Order statistics, okay? Order statistics. Okay, so how on earth would we ever actually determine like what the distribution of these guys are relative to the original random variables? Okay, so that's going to be our goal, is to kind of determine what the distribution of the y's are given the distributions of the various x's. And then we'll do an example and see how all of this plays out in practice. Okay, so the goal, okay, here's our goal. Okay, so given CDF capital F of x for the x's, so x1 through xn, what are the CDFs and densities, okay? And density and densities, okay, for y1 dot 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 yn, okay? Okay, and by the way, so we have the CDF for the random variables, and we're also going to let little f of x equal to capital F prime of x be the common density, right? So, I mean, the CDF is the same for all the x's since they came from the same distribution. And as such, they would also have the same density. So this is the common density for x1 all the way through xn. Okay, so our goal is to figure out what this CDF actually is. Okay, so that's going to be our overall goal. Okay, what is the CDF for these things? So let's work with y sub r. Okay. Okay. So this is equal to the rth order statistic. Okay. So that's the rth ordered statistic. Okay. All right. So let's let g sub r of y equal to the probability that y sub r is less than y. Okay, so this is the CDF for the rth order statistic, and assume that, you know, capital F of X is between 0 and 1 for A less than X less than B, okay? And that what? F of A equals 0 and F of B is equal to 1. Okay, and okay, so this looks like a lot of assumptions, but they're all just very basic things that we have to list out before we do this analysis. Okay, and one thing I want to note is that, you know, technically speaking, I might have a CDF that actually never reaches 0 and never reaches 1. It just constantly, as I go to the left, it's getting closer and closer to 0 as I go to the left, and it's getting closer and closer to 1 as I go to the right. So I'm going to permit A to be negative infinity and also B to be plus infinity are permitted. Okay, so those are permitted things. Okay. All right, so we have this guy right here, and we want to figure out what's going on with this. So this guy right here is the CDF of Y sub R. Okay, if I can figure out what the cumulative distribution function is for Y sub R, you know, we're in pretty good shape, because then I can find the density for Y sub R simply by taking the derivative. Yeah. Okay. So let's, this is all very abstract what we're doing here, but we're going to be able to pull it off. Okay. So let's start this computation. So G sub R of Y equals, okay, the probability that Y sub R is less than Y. Okay, so this is the rth order statistic. Okay, and what about the event Y sub R is less than Y? What does that mean? That means that at least R of the variables x1 through xn are less than Y. Right? I mean, think about it for a second. YR is the rth smallest among the x's. And if Y sub R is less than Y, that means that at least R of the x's had to be smaller than Y. Yeah? At least R of those had to be smaller than Y. Okay? So this means, so this is equal to the probability that greater than or equal to R among x1 through xn are smaller than Y. Okay? All right. So how in the world are we going to recast this thing? It's easier. Okay, so now we can actually just think about the x's. So what we can do here is we can define the probability of success. Okay, so for xi, define the probability of success to be equal to the probability that xi is less than Y, which, by the way, what is that? Well, that's just going to be capital F of Y. Is it not? I mean, after all, that's just, you know, that's just the CDF of xi. Okay, the probability of xi less than Y, that's just going to be the CDF, the cumulative distribution function for xi. Okay, then what is this? Okay, what is this thing right here? Think about it for a second. Okay, so what's this equal to? Well, that looks like basically, so it looks like if I were to introduce a if I were to introduce like a binomial random variable, it looks like I'm actually trying to compute something to do with a binomial random variable. Okay, so let's go ahead and do that. So what if I went like this? Let's actually define. Let me just do this up here. Define. Oh, I don't know. I've used x's. I've used y's. I'm going to use z's. but please don't think that this is like some kind of, that Z is some kind of standard normal random variable. That's not true. So define Z to be distributed as binomial, binomial with n trials and proportion of success P equal to F of Y. Okay? So think about this. How is that going to impact this probability that I'm going to try to compute here? What's the relationship between Z and needing to have at least R of these be less than Y? Well, that means I can think of these as independent trials. Each of the X's is like an independent trial. Is X1 less than Y? Success or failure? Is X2 less than Y? Success or failure? And I simply have to go through and perform those Bernoulli experiments one at a time, and they're independent. And so this probability is the same as Z being equal to or greater than R. Okay? So Z is just going to count the number of those Xi's that happen to be smaller than Y, and that's what I consider to be success. Okay? Now here's the thing. What's interesting is I can actually write down a formula for this, since we're like experts, since we're complete and utter experts when it comes to the binomial distribution, are we not? So let's write this down. Is this not just going to be the sum of what? Well, I need to have at least R successes. That means at least R of these Xi's were smaller than Y. That's what it would take for the rth order statistic to be smaller than Y. This is an if and only if. Okay, so this is K equal to from R all the way up to N. Okay, what was the probability distribution for that? So this is so interesting, right? We're sort of using a discrete distribution to get at this continuous distribution. Okay, so it's going to be N choose K. I want to sum all those together, and then it's going to be the probability of success raised to the K. All right, well, what's the probability of success? Well, that was F of Y raised to the K. Okay, those were basically the K X's that were smaller than little y. All right, times, okay, times what? What's the probability of failure? Well, it would be 1 minus F of Y raised to the N minus K. Yeah. Okay, and that's it. Unbelievable. We have the formula written down right there. Okay, so this is GR of Y. Okay, let me just kind of highlight this so that we can see it in all of its glory here. Okay, I have this. That is the CDF for the rth order statistic, right? So this is the CDF for the rth order statistic, Y sub R. Okay, that's pretty remarkable for sure. Now, I also want to get the density though, just so that I can have everything in sight. I want to also have the density. How am I going to get that? Well, I'm going to take the derivative of this thing. And really, to take the derivative of this thing, it's a little bit more convenient to write this in a slightly different way. And so we'll do that on the next little board here. But this flat out is the CDF for the rth order statistic. And I don't care what distribution you threw at me from the beginning, as long as you have n independent, identically distributed, that means they're from the same distribution, and they are continuous, so that I don't have equality causing a whole bunch of problems. This is the CDF for the rth order statistic. Okay, that is an amazing thing to behold. No doubt about it. So let me write this thing up here for us. Okay, just for computational purposes. Okay, so GR of Y, the CDF for the rth order statistic, was sum K going from R to N of what? N choose K. Capital F of Y to the K, and then 1 minus capital F of Y raised to the N minus K. And I'm going to write this in a slightly different way. I'm going to peel off the very last term here. This will be sum k going from r to n minus 1. Okay, if I plug in k equal to n choose n is just 1. Okay, let me finish writing this, the terms that aren't going to get peeled off here. Okay, 1 minus f of y to the n minus k. Okay, and this is going to be plus, what is the last term? Well, it's the k equal to n term. The 1 minus f of y thing is gone because it's raised to the 0 power. And it's n choose n, which is 1. So it's going to be f of y to the n power. Okay? It's f of 1 to the n power. Okay. And what about, so what do we want? We want the density of y sub r. So what is it? Okay. Well, it's going to be, so g sub r of y is how we'll denote that. Just for convenience, this is going to be g sub r prime of y, okay? And the reason I kind of wrote the CDF this way is so that I have non-trivial powers on capital F of y and 1 minus capital F of y in the sum, okay? The powers are always at least 1 for each one of those factors now. The only one that didn't follow that was the very last term that corresponded to k equal to n, which is why I peeled that one off. That way, in what I'm about to do, you'll see you'll see that I really wanted to know that there were two factors. There was two factors, one that had an f of y in it, one that had 1 minus of an f of y in it, because we're going to have to apply the product rule when we take this derivative. Okay? Because look, there's in that sum, I want to know whether I have a real actual product or not. Okay? And that's why I peeled off the last term, to make sure that I know that there's both those terms in there, non-trivially, and I have to apply the product rule. Okay? So we have to apply the product rule to that sum part. Okay? So what do we get? Well, it's going to be sum k equal r to n minus 1. Okay, so I go the derivative of the first, right? Each one of these summands, I'm going to go to the derivative of the first times the second plus the first times the derivative of the second. Okay? And I have the n choose k is just a constant sitting there. So it's going to be the derivative of the first times the second plus the first times the derivative of the second. So this is going to give rise to two separate sums. Okay, and at first this looks like, annoying, but, just bear with me. So this is going to be derivative of the first, so the k comes down, k times f of y to the k minus 1. And I know that k minus 1 isn't, like negative or something, because r was at least 1. Okay, and then this is going to be times, well, it's times the derivative of what's inside, right? I'm doing the derivative of the first. What is the derivative of capital F of y? Well, it's going to be little f of y. Okay, so let me just put a little reminder in here. This little f of y is really capital F prime of y. Okay. Okay, and then it's times this other thing, 1 minus f of y to the n minus k. Okay, so then it's plus, okay, so that was the derivative of the first times the second, plus the first times the derivative of the second. Okay, so that's going to be plus sum k going from r to n minus 1. Similar kind of game here. N choose k. The derivative of the second, it's going to kick down an n minus k. All right? It's going to kick down an n minus k, and then it's going to be f of y. So this is f of y to the k, and it's going to be 1 minus f of y to the n minus k minus 1 times the negative of f prime of y. I have to use the chain rule here. And that's going to be negative f of y, little f of y. Okay. There's a negative sign right here. That is very important. Okay. So I did the derivative of the first times the second plus the first times the derivative of the second. Okay. And of course I have to take the derivative of this remaining term right here. And what is the derivative of that remaining term right there? Well, that's just going to be plus n f of y to the n minus 1 times f prime, capital F prime of y, which is little f of y. Okay? All right. So that looks incredibly obnoxious and unwieldy, but I am telling you that there is a light at the end of the tunnel here. Okay, I'm going to write some stuff on the next board. I'm going to copy this down and I'll be right back. All right, we're back. So all I did was copy down the formula for the PDF, the density for the Rth order statistic from the previous slide, and where we got it from, namely from differentiating the CDF that we came up with. We ended up with this horrible looking formula because we had to use the product rule, okay, and we peeled off the last term from the CDF because that was the only one that that wasn't a true product. All the other ones have at least one f of y and at least one minus f of y multiplied together, so that we truly had to use the product rule. Now, what I've done here is I've made a couple of notes, because we keep seeing this term right here, n choose k times k, and we see this term right here. So what I did here is, in this note, I've said, look, if you just write out the formula for n choose k factorial, there's a factor of k that's going to cancel. Okay, and incidentally, k is in range where there's no funny business going on. K is not like 0 or something like that. K is bigger than or equal to 1, because remember, R is the Rth order statistic, and K is equal to or less than n, or it's actually less than n. Okay, so there's no funny business going on here. N minus K is at least 1, and K itself is at least 1. So this computation that I have here, that I'm showing that n choose k times k is equivalent to, is totally legitimate. Okay, so n choose k times k is equal to n factorial over k minus 1 factorial, if we cancel that factor of k, times n minus k factorial. And similarly, n choose k times n minus k is n factorial over k factorial. And then n minus k factorial, we just cancel one factor of n minus k to get n minus k minus 1 factorial. And then what I've done down here is I've taken that into account in each one of the sums individually. Okay, so the first thing I'm doing here is I'm looking at this first sum. Okay, so this sum is this sum right here. Yes, that sum is that sum right there. And I'm just using this first identity right here. Okay, I'm using this first identity right here, and I'm writing out what the sum actually is. Okay, so the first term, if I take k equal to r, it's just going to be n factorial over r minus 1 factorial times n minus r factorial times, whatever you get if you plug in k equal to r. And we get that, and we just go on through and we get all of these summands. Okay? And similarly, I'm going to take this second formula right here, and I'm going to use it in this second sum right here. Okay? And that's going to happen on the next slide here. All right, so just know that all that I did was I just straight up plugged in what k was equal to from r up to n minus 1 to get this first expanded sum right here. And I'm about to do the same thing in the second one. Okay, so that's what's over here. I basically just use the formula for n choose k times n minus k, and I end up with this. And here's something that we immediately should observe. And let me get a little bit of a red pen here. So look at this. Look at this first sum right here, or this first summand right here. Okay, does that match anything on the previous slide? And one thing I would point out is that there is a negative sign here. Okay, there is a negative sign sitting right here. So does it match in an opposite sense something on the previous slide? And the answer is yes. Okay, it actually matches this term right. Wait, hold on a second. I kind of lost it there. So r factorial n minus r minus 1 factorial in the denominator. Capital F is being raised to the rth power. 1 minus f is being raised to the n minus r minus 1 power. Okay. What does that match? Well, it matches this term right here. So this term right here cancels with this term, this first term over here, because of that minus sign. And a similar thing happens for higher terms. Okay? We just say this term right here is going to cancel with the second term over here. Okay? And the same thing is going to happen for all the terms but the last one. Okay? For all the terms but the last one. So all of these things in the dot, dot, dot part are going to cancel all the terms beyond the first one over here. They're offset from one another by one thing here. So all of this dot, dot, all of this stuff here and all the way down to the end. There was the same number of terms in each summand, and the second term canceled with the second term in the first sum canceled with the first term from the second sum, etc. So this first term survives, and this last term over here survives, right? So this guy survives, okay? And over here, the first term survives, okay? The first term survives. There it is. All right. So let's see here. That means that actually all of this nasty sum right here, this whole nasty sum, the whole nasty sum cancels, like almost everything cancels except for the first term from the first sum and the last term from the second sum. So what do we get? Well, let's kind of bring all these pieces together. So here we are. All I've done is copy down the first term. So let me just kind of highlight this. This right here is the first term from the first sum. This right here is the last term, right? So this is exactly this term right here. It's the last term from the second sum. But then remember we had this extra term right here that was tacked on. Yeah? This term came from the one that I peeled off before. Okay, so over here. Just a second, my screen is struggling. Okay, so over here, if you look at this, it's this term sitting right here. That extra term that was sitting there. Okay, so if I go over here, look at this. This guy right here comes with a minus sign, whereas the other one has a plus sign. N factorial over n minus 1 factorial, that's just n. So these guys cancel each other also. They're gone. And therefore, this right here is all that's left from that derivative. We had like this kind of collapsing sum of sorts that took place. Everything in sight ended up canceling. And we ended up with this nice formula for the PDF of this particular thing. Okay? So that's amazing. Okay, so I'll be right back. I'm going to actually copy that down on the next board here. And here it is in all of its glory. We have the rth order statistic, YR. There is the CDF sitting right there. Okay, and remember we kind of got at that by thinking about, success, meaning that, the ith random variable x sub I was smaller than y itself. That was success until we used the binomial distribution to help us write down this cumulative distribution function for the rth order statistic, because we have to have at least r of those x's being smaller than y. So therefore we counted success and failure that way and applied the binomial distribution to our advantage. Okay. And little g sub r of y, that's the density of this thing, we got by taking the derivative, and tons of stuff canceled. All except the first term from that first gross sum. Everything canceled except for that first one. And this is the density of that thing. Now, it might seem a minor miracle that that thing is going to integrate to 1, but it will. And by the way, the assumption was that the x's were only producing stuff between A and B. And so we can take our little y to be something between A and B also. Okay? Because that's the only place we're going to get anything for the order statistics, if that's the only place that we were getting things for the x's in the first place. Okay? So I think I'm going to stop right there for this part of the lecture, and we'll actually do an example using this formula to kind of finish this particular topic off. I think you'll really enjoy seeing this thing in action somewhere. All right? That's all for now.